Okay, we show you the all the formula, like what will be the formula. All the formula I summarize right over here. This one is volumetric strain. This is the formula. In short form, it will be like that. For incompressible flow, volumetric strain will be 0. Then for rotational flow, this is our vector. Omega s, rotation along x-axis, y-axis, and z-axis is omega z. And this is the rotation in xy plane. This one rotation in yz, and this one is xz plane. And vorticity equal to twice of rotational vector. That's why they put a 2 over here, because you multiply by 2, ultimately this half will be gone. Okay. If we are not putting half over here, then vorticity will be equal to the rotational vector, right? But anyhow, they define it like that. Twice of rotational vector is called vorticity. That's why they already put half over here. And in short form, you can say this is the vorticity, and half of curl V is the rotational vector. And angular deformation is this one in xz plane, this one in yz plane. So this is the formula we have summarized. Now we need to know two things. Actually, how all the software, ANSYS, FEMAP, SolidWorks might have some. You can do some little bit simulation. I'm not sure. So how they show all the contour, all the streamline after you run a model. But inside, they use a lot of equation for streamline. And streamline, what is the definition of the streamline? It shows the direction of velocity at any point in the streamline. This is the streamline, direction of velocity tangent to the streamline. That means along a streamline, a fluid particle is moving, but it don't give you the amount of velocity. What is the velocity? It's giving you only the direction. Okay, and the velocity at each point, magnitude is changing, magnitude and also direction. But streamline only give you the direction of the fluid flow, fluid particle flow. So to have you like to see the streamline after run, and also you like to see the velocity pattern, that what will be velocity of the fluid particle. For example, in a pipe flow, all the fluid particle is right over here, right? So how they moving? They're moving along a streamline. If follow is laminar, okay, low velocity follow streamline. But velocity, like this one, will be after time t, still it might be with the wall due to the viscosity and friction. But this one might travel right over here. This one, say, coming over here. So all the particle, you might get this kind of profile. So if you join all this line, this is get velocity profile. In this velocity profile, you see right over here in this portion, only this portion, all three fluid particle might have the same velocity. So this is the streamline, and this is the actually, if you call it, we call it velocity profile. But just think this is the velocity line. Okay. So definition of streamline we already learned, right? Now, what is the how we'll define the velocity line? So we need to know two more definition. One is velocity potential function. What is the velocity potential function? And also know what is the stream function. These two things we know. Is not the streamline, that is called stream function. Stream function mean this represent the equation of a streamline, okay? And the potential function represent the velocity line. So these two definition we need to learn. Number one is stream function, then velocity potential function, okay? So let's see, learn the definition, and then we learn what is the application of these two function, why actually needed. Okay. Velocity potential, it is represented by letter phi. And it's saying it is defined as a scalar function. That means it don't have any vector. Function, scalar function of space and time. That means this phi is a function of x, y, z and also t, because function of space and time, such that its negative derivative. So if you make it derivative like along x-axis, then derivative will be del phi into del x. Along y-axis, del phi by del y, z-axis del phi by del z. So it's saying its negative derivative with respect to any direction give the fluid velocity in that direction. So del phi by del x, you making derivative along x-axis. That means this negative derivative is giving you velocity u. So similarly, minus del phi by del y equal to v, that means velocity along y-axis. Similarly, minus del phi by del z, that will be equal to the velocity component along z-axis. Now, if is a steady flow, that means nothing is changing respect to time. In that case, phi will be function of only space, x, y, and z. So now we got the velocity in terms of phi, right? Now, for incompressible flow, if flow is incompressible and steady, that means phi is not function of time. In that case, our continuity equation is this one. If you look in the previous slide, for incompressible flow, this is called right over here volumetric strain, right? But in the previous lecture, we derived the continuity equation, right? For incompressible flow, continuity equation become like this one, same. If flow is incompressible, then del rho by del t equal to 0. And you have this one then. So for incompressible flow and steady flow, we know this is the continuity equation. Now, this u, we can put it over here, u, v, and the w. If you put it over here, then your equation coming, this is u, this is v, and this is w. So ultimately, your equation, continuity equation coming this one. And if you try to remember your math class, this equation is called Laplace equation, this one. And in short form, Laplace equation, you can write this one, del square phi equal to 0. So if I give you a function phi, I'm saying phi equal to For example, I might say phi equal to x square plus xyz minus 4xz square, just for example. Now, you need to, you see phi is a scalar function. This is not ijk here because it is not a vector. So how did you know that this flow will be irrotational or incompressible? This phi, you figure out del phi by del x, then figure out, at first find this value del phi by del x. You differentiate one more time, then you get del square phi by del x square. Similarly, you find del square phi by del y square. Then you put it over here. If it satisfies this equation, that means flow is irrotational and also flow is incompressible and irrotational. And sometime in some book refer as a, if you have a irrotational flow, sometime it is called potential flow. Okay, so I can confuse you if I put a question, I give you a phi and prove that this is a represent a potential flow. Yes or no? That means don't be confused. That means you have to satisfy the Laplace equation. Okay. So in phi, you see, coming from Laplace equation. If you have the Laplace equation, then you can say the flow is rotational or irrotational. And other thing, if phi is given, you can easily figure out the u and the v. Say, for example, I am saying phi equal to x square plus y square minus z square. Just example. What will be the u? U equal to minus del phi by del x. You figure out from here del phi by del x, differentiate both sides, then say this equal to minus u. But obviously there will be one constant. Then you can figure out the v if you differentiate respect to y. Okay. So this is the properties of potential function phi. Now, if what is our rotational vector? Rotational vector is this one. Wx equal to this one. This is Wz. Now, you see, we know the u and v. This is u, this is v, this is w, right? So this u and v and w, this we can substitute the w, v, u by those equation. Then we will get, for example, omega wx or omega x, that means rotation around x-axis is become this one. This is w equal to minus del phi by, we know that omega, I'm sorry, omega equal to, or w equal to minus del phi divided by del z, right? So right over here, what will in this w you replace by this term. So you have minus del square phi del y del z. Similarly, what is the v? V equal to minus del phi divided by del y. So you replace by v, you will get this term. Similarly, replace u, w, you get this term, and vu, you get this term. So if phi is irrotational, then what will happen? This equal to 0, this equal to 0, this equal to 0, right? So If this is 0, that means this term equal to this term, and this term equal to this term, and this term equal to this term. That means if you have a phi, then you can use this Laplace equation, and also you can use the rotational vector equation. Then you prove that there is no rotation of the fluid element. So flow is irrotational. So you have two options. Okay. Then we need to know the stream function. What is the stream function? It is also a scalar function. That means it is not the, it don't have any vector. Defined as a scalar function of space and time. That means you have x, y, z, and t. This is called psi. Stream function psi equal to function of space and time. That means x, y should be right over here, should be z2. Okay. In space and time, if is two-dimensional flow, such that partial derivative with respect to any direction. Right here, remember that stream function or streamline should be in one plane, in a single plane, either xy, either yz, or either xz plane. So that means the stream function will be function of either x, y, and t, or y, z, t, or x, z, t, or only three function. And if it's steady function, then it will be function of x, y. So that's why it's saying the stream function is defined as a scalar function of space and time in two-dimensional flow, not the three-dimensional flow. If you look in the potential function, is function of x, y, z, and t, but stream function only function of two variable, because it represents the streamline, and streamline always remain in single plane. Okay, that's why they're saying that stream function is a scalar function and it is function of space and time in a two-dimensional flow, such that it partial derivative respect to any direction. Partial derivative with respect to any direction. So let's figure out, I like to say del psi by del x. This is his partial derivative along x-axis. So what it will give us? It's a any partial derivative with respect to any direction gives velocity component at right angle in that direction. So in x along x-axis, I am making derivative del phi by del x. So what will be the right angle direction? That means along y. So that means del phi by del x, this equal to v, velocity component along y direction. Similarly, if I make del phi, del psi by del y, that means I'm making derivative along y-axis, and perpendicular direction is x. That means it will give you velocity, x velocity u. Okay. Now, you see, so right over here, they are saying, let me erase the box. Right over here, del u by del psi is mass u, mass with us, right? This is u minus they put v. We say only del phi by del x, that they put a negative sign in front of it. It has a specific reason, because In the two-dimensional compressible flow, we are saying over here that stream function for two-dimensional flow. So we need to make sure that it satisfy the continuity equation. So this is our continuity equation in two-dimensional flow. So summation of these two has to be 0. Right over here, there is a mistake. This will be del y. Okay. Del u by del x plus del v by del y. This summation will be 0. Now, if you del u, this u you put it over here. So you are getting del by del x. In the bracket, you will have del psi divided by del y. So what is you getting? Del square psi by del x del y, right? They are putting over here del square psi del x del y. Now similarly, you substitute the other term. That will be del square psi del y del x. You see both is same. This term is same. So if you are not considering minus over here, then the equation, quantum equation will not be satisfied because it will be the plus sign over here. So that's why in a definition of V, they put negative sign. That means del psi by del y, you making derivative along y-axis, but it represents the velocity along x-axis u. Similarly, del psi by del x, that means you making derivative along x-axis, so it represents the velocity along y-axis v, but to satisfy the continuity equation, we need to put a negative sign over here. Okay, that you need to remember. Okay, so stream function satisfy the continuity equation. That means if stream function is not satisfy the continuity equation, that means it is not the real stream function. It's something wrong in the equation. Say I am giving you that psi equal to x square plus y square or 2xy, for example. If this, you figure out del psi by del y, figure out the u, you figure out the v, then or you put the, try to match this equation. From here, you figure out value of u. What is the u? Del psi by del y. So your u will be del psi divided by del y. What is that value? X0, then it will be 2x only, right? That will be u. Now this u you put over here, then del u by del x equal to 2. Similarly, you figure out this value, then you see that it is satisfy continuity equation or not. If it is satisfy continuity equation, then you can say, okay, this is the right function for the streamline. That means this is the accurate stream function. Okay. Okay. Now we like to check that what is the stream function, how it is look like. Okay. So you see stream function, it is two-dimensional flow. So that means a stream function psi equal to psi of xy. Now I like to differentiate this function. For example, if you differentiate, you have dx, you have u into v. How will do it? Same thing over here. Okay. So if I differentiate the both side, this left side will be del psi, right? So our equation will be, if I write in the top, del psi equal to, you make derivative this one, say respect to x. So you are making del psi divided by del x into, there will be del y, then plus you do del psi by del y into, right here will be del x. I think I am wrong. This is del x, this will be del y. Okay. And it is already, I think I show you somewhere already, but I didn't go through it. At the beginning, we show you some math formula, right? This one in, I think, in your lecture sheet 5, you know, show you. Let's see, I have over here or not. Right over here, we have it. You see, f is a function of x, y, z, and t. Now, how did you figure out the derivative of df? You see, df equal to del f by del x, then multiply by dx. Del f by del y multiply by dy. Del f by del z multiply by dz. Del f by del t multiply by dt. So same thing. We have, instead of f, we have psi. That we have psi equal to psi of xy. So d psi will be which value? We can say d psi will be d psi, if you differentiate with respect to x, right here will be dx. Plus, if you differentiate respect to, then next derivative will be y into dy. Okay. Similarly, we can differentiate respect to, this is psi, we can differentiate phi too. So let's go back to our previous slide. Okay, we are right over here. So this one, we make a derivative. D psi equal to d psi by dy delta y into dy, d psi by dx delta x into dx. Okay, now this is our derivative. Similarly, we know that phi, potential function, equal to function of x, y, z, right? So similarly, we can figure out value of d phi by similar formula. We can figure out. Okay. So what is our intention over here? Our intention over here, that how is a stream function along a streamline, how it is look like, that we'll try to figure out. So we know this one, right? Then from the definition of streamline, I think might be somewhere I put it in the slide. Let's see. I didn't put it. Okay. In lecture sheet, this is 6. If you look in the lecture sheet 5, we work with stream function. I'm sorry, streamline. As per definition of the streamline, we found this one, that del x divided by u equal to dy by y velocity component equal to dz divided by w. You remember, this is the streamline. We make a line over here. This is dr, this is dy, this is dx. Then we show it that for streamline has to satisfy this equation. So that's why you put over here. As per definition of streamline, we know this one. So from here, what are you getting? Del u by, just multiply u into dy equal to v into dx, right? Now we have this equation. Now what is the u? U equal to del psi by del y. You look over, this is u, this is v. This uv we put over here. This is u and this is v. V equal to minus del psi by del x. So this minus become plus. So this equal to 0. Now this value you put it over here, you see. So what we are getting actually? D psi equal to 0. That means if you integrate both sides, what are you getting? Psi equal to constant. That means along a streamline, the value of psi is constant. If we know the function psi, we can plot constant line of psi to provide the family of streamline that are helpful in visualizing the flow pattern. Say psi is a constant. So psi equal to 1.33. Say I like to make a graph. Say along this line is x-axis is psi, this along this axis is phi. So psi equal to 1.33. What will be the line? Straight line, right? Along straight line, this will be value of psi. So along a streamline, psi is constant. You remember that one. Now, what is our intention actually? Our intention actually to show a flow pattern. I like to know which way fluid is flowing. Say, so this is my streamline. I can say this is a nozzle, kind of nozzle. So this is a streamline. So fluid flowing along the streamline. And this streamline we can figure out, right? By the equation, this is streamline. And I like to know where is the velocity line, right? Fluid particle right over here. All the fluid particle have a same velocity. Right over here, along this line, fluid particle will have same velocity. Similarly, along third line, all the fluid particle have the same velocity. Velocity magnitude will be same along all the location. So how we'll figure out this line? This line is phi. So if I know the phi equation of phi and equation of the psi, then I can plot it. Then you can see the nature of the flow. Where is the velocity high? Where is the velocity low? How the streamline is look like? They are intersecting or not, or they are parallel. Okay. So my intention to figure out a relationship between the phi and the psi. See right over here, they are intersecting. So what will be the angle when they intersect? Is it 90 degree or is it 45 degree? If you know the angle, then it can intersect anyway. I can say it can intersect this one, or you can go like that, right? So that is our intention. Now over here it's saying the difference between two streamline. So you have a stream function in this one. Say we have a stream function. This is psi 1, this is psi 2, and this is psi 3. If you figure out the difference between two streamline, that is psi 1 minus psi 2, this represent the flow rate, volume flow rate. And it can also define as a flux or flow rate between two streamline. And in it will be meter cube per second. That means discharge. And we say sometime is Q in per unit thickness of the flow. Say you are looking the flow at the top surface of the river. Then you can say at the top surface, this streamline is valid until depth is 0.5 meter or 1 meter. Then you can say phi 1 is phi 2, you got 4. So your result unit will be meter cube per second per meter of thickness. Okay. So existence of psi mean a possible case of flow. So if there is a psi, if psi value is 0, what does it mean? Q0. Q0 means there is no flow. So if there is a some value of stream function of psi, it indicates that there is a flow. Now, I already told you that I like to figure out what is the relationship between two lines, phi and the psi. So you see from the definition of phi, derivative along a axis, negative derivative represent velocity in other direction. So if you make d phi by dx, then put negative sign, it will give you velocity u. Del phi by del y, it will give you, put minus sign, that will make it negative derivative. It will give you velocity in that direction. That means along y direction. This is coming from the definition of phi. That means velocity potential function. And what is the definition of streamline? You make derivative along x-axis, del psi by del x, it will give you velocity in 90-degree angle. So you're making derivative along x-axis. So it will give you velocity along y-axis. That means v. So v equal to minus del psi by del x. Similarly, you are making derivative along y. So it is giving velocity along x-axis. So u equal to this one. Just refresh it again. And you remember, what is the negative sign over here to satisfy the continuity equation. So streamline, when you say you are a researcher, you like to define a streamline. When you define a streamline, then you need to make sure that is satisfying the continuity equation. Okay. Now, my intention to how these two lines intersect each other. If I make a graph, say along this direction is psi, along y-axis is phi. If they intersect, then what will be the angle between them? So for example, this will be phi line and this will be psi line, right? Then what will be intersection, angle of intersection between two lines, or what is the relationship? That we try to figure out. Now you see this one, we can derivative del phi. So del phi will be del phi by del x into dx, del phi by del y into dy minus this one, right? because this equal to del minus u. You say d phi by dx minus u. So u into dx. And del phi by del y equal to minus v. So we are getting this one, d phi. Similarly, psi stream function is function of xy. So its derivative del psi by del x into dx plus del psi by del y into dy. Now, what is this value? Del psi by del x, you see, minus v. So I got minus v over here into dx. Similarly, this equal to u. So I put u over here. Now, along a streamline, we already show you before that psi is constant. Psi is constant. That means difference of psi between 2 points will be how much? 0. So no difference of psi. So this one is 0. I can say this equal to 0. If this equal to 0, this value, then I can figure out the slope. How I can figure out? I have from here, if this equal to 0, I can say v into dx plus u into dy equal to 0, right? And from here, if I rearrange, I can figure out dy by dx. And dy by dx, I'm getting this one. And what is the condition? Psi has to be constant. Similarly, if along a line phi is constant, then this will be 0. So from here, I can figure out value of dy by dx. So dy by dx, and I am saying phi constant. That means this dy by dx for a line where velocity potential function phi is constant. And this phi, we are getting minus u into v. Now we see, what is the dy by dx? Dy by dx actually slope of the line. So if I say this is m1 psi, this equal to, you are getting v by u. And m1 phi or m phi will be how much? M phi, slope of the phi line, we are getting minus u by v. Now multiply these two, m phi into m psi, then you are getting minus 1, right? If you multiply this one and this value. So if slope of two line is constant, then what does it mean? That means they intersect each other at a 90-degree angle. M1 into M2 equal to minus 1, then slope is they intersect each other in perpendicular direction. So it's a product of slope psi constant line and velocity potential line phi equal to constant line is negative. That means the slope of two line is minus 1. So both lines are perpendicular where they intersect. The line of constant phi, also called equipotential line. Equipotential line mean along that line, velocity of the fluid particle will be same. So you see in the bottom, you see a group of streamline with pink color with arrow. And this is a equipotential line with dotted line, black dotted line. And they intersect each other with 90-degree angle. From this, that we already proved that when they will intersect each other at angle 90-degree. So what does it represent? Represent that the velocity of fluid particle, right, all those points will be same. Say, for example, 2 miles per hour or 2 meters per second. And this one right over here might be 4 meter per second. All the fluid element, if you write over here, you will be all have same velocity. Similarly, right over here will have same velocity, but velocity at two line should not be the same. So right over here, these 5 fluid element will have the same velocity. Similarly, if I draw over here 5 fluid element, their velocity will be same. So if you know the stream function psi and potential function phi, you can plot them. Then you will get a graph like a net, right? Fishing net. So that's why that graph is called flow net. And normally, if you do the simulation in ANSYS or other software, you will see you can plot this kind of line. Then you can see where velocity is the equal, how the streamline is going. Okay, so flow net is consist of a family of streamline and equipotential line that represent graphical flow pattern of the flow for visualization. I told you before that flow visualization, flow over a sports car, flow over a aircraft wing, how we can figure out? You cannot see here in your eye. So you design a shape and you look in front of the shape or front of the sports car, but you cannot figure out how air is flowing. But what you can do, you can make a model of your product, a ship or a airplane. Then you put in the wind tunnel, and front of the wind tunnel, if you are able to put some, or if you are able to make some color smoke, then you can see how smoke is passing over the structure, over the aircraft or over the racing car. This is one option. Other option, you can make a small model, but shape has to be same. You need to just scale down. Then in that model you run in the ANSYS software. Then you can see how it will show you all the lines, streamline, how is flowing over your sports car. Okay. So you need to know actually the fundamental things, that what is the stream function, what is the potential function. What I'm saying, you will not develop a code in ANSYS, might be, say, ANSYS, whoever company, they sell the ANSYS, they have group of people, they inside, they develop the code. So if you got the opportunity to work there, you might develop a code to generate the stream function, potential function, and how will be the flow net for a particular situation. You can work on it. But as a, say you go for higher study, or you working in a company, they make special boiler or a vertical tower. For example, in a fertilizer factory, that liquid nitrogen is fall down from the top, okay, from the top, and air flow upward direction. When he's coming down, gradually he cool down and make granular object, that is fertilizer. Now, if you like to figure out how is the airflow look like, say you might have a vent right over here, right over here. So you are coming through this vent, then is getting out over the chimney. So you like to see how they're flowing, how we can figure out. You need to have the streamline. You're able to plot the streamline, then you can visualize the flow. Okay. So far, any question? Anyone? No question? Hello? Okay. In some slide, I write down this term, note. That means this will not come in the exam, but I put it to understand the derivation. Okay, so I can skip it. This slide, same thing is not. So I'm skipping. This one is not. I just put it that this is the uh, divergent deep. Okay, so if, for example, if velocity of a fluid is function of x, y, z, and t, then how we can figure out the acceleration? So right over here is the this one. Okay, what is the acceleration? dv by dt, but v is the function of x, y, and z. Then what will be the formula that I put it over here? Similarly, velocity. If you have velocity, three component, x component u, that means u v w. If you have a velocity, then remember your acceleration will have three component. That one is x component, that is y component, and in the bottom we have this one is z component along third axis. Okay, and you see that acceleration, it have fourth term. This one is the derivative v into del u by del y, w into del u by del z, but all of them have a function del u by del t. If it is a steady flow, then what will happen? Del u by del t will be equal to 0. Now, the material derivative. You just remember the material derivative has two parts. One is called local part, del by del t. Other one is called advective term. That means divergence of vector, or sometimes it is called convective term. The material derivative is composed of a local or unsteady part. That means del by del t, because it depends on the time. That's why it is called local derivative. And the other term, this term is called convective term or advective part. Okay. So if I say what is the material derivative, this is the definition. Total operator d by dt, sometimes give a special name, that is called material derivative. It is formed by a fluid particle as it moves through the flow field. And other name of the material derivative is total derivative, Lagrangian derivative, Eulerian derivative, sometimes is called substantial derivative. And material derivative equal to this one, and it has a two part. This part is called local part or unsteady part, and this one is called convective part or advective part, because this one represents the motion of the fluid along all three axes. So that's why it is called convective part, because convection is depend on the velocity of the fluid. So just read the definition from here. This one actually we don't need it. Same thing, this one you don't need it, just you read the formula on time. All the formula is summarized again over here. This is Laplace equation. Okay. Okay. So now we can start with lecture sheet 7. Before I start 7, any question? Any question? Any comment?
No, sir.
No? Okay, so I can continue, right? My screen. Stop share. 1 second. Okay. Did you see lecture sheet 7, the PowerPoint?
Yes, sir.
Okay. Uh, you should not be scared because same stuff I put it over here. Actually, name of this chapter is problem on rotation of fluid particle and stream function. So no theory over here, but I put it this stuff to remind you. That's why I put a note over here with the red color. This one also note. That means same formula. This one is same formula. You see now this is a problem, and so far you already observed that there are a lot of small differential term or derivative and formula. Now we need to know what is the application of it. Okay, so you see problem 1, in a two-dimensional incompressible flow. Incompressible flow, that means it satisfies continuity equation, has to be that the fluid velocity component are given below. U and V is given. Show that flow satisfy continuity equation. You need to make sure flow is satisfy continuity equation, and also obtain the expression for stream function and the flow potential function. That means you need to figure out the psi function, stream function, and also you need to figure out the phi. And magnitude of u is given in terms of xy, v is given in terms of xy, and you say you need to show it satisfy continuity equation. So what is the continuity equation? Right, what it's saying is incompressible flow. So your continuity equation is del u by del x plus del v by del y equal to 0. So from here you figure out del v by del x. From here del v by del y. Then put it over here. If it satisfies this equation, then you can say it satisfies continuity equation. Now, how we'll figure out the function psi and function phi? You can figure out, for example, what is the relationship between this phi and the u. You say negative derivative along x-axis of phi, this derivative, I'm making negative, put negative sign. This equal to what? It giving you velocity in the same direction. That means this is u. Similarly, if you make del phi by del y, it will represent v. So from here, you see del phi equal to what you say? Del phi equal to u into del x. You getting from here del phi equal to minus u into del x. Now, value of u equal to this one. You put it over here. They indicate both sides. This way, you can figure out the value of phi and value of psi. Okay. And now let's see how we can solve it. Before we solve, let me show you the another problem. It's the same thing. It's saying velocity component in two-dimensional flow field expressed by this relationship. So we have the magnitude or function of u, function of v. So you need to figure out, you need to show flow is incompressible and irrotational. So if satisfy the continuity equation, then flow will be incompressible. Then you need to figure out, show what is the condition of irrotational. Then it's a obtain expression for function phi. You need to figure out psi and you need to figure out the function of phi. Okay, so we'll solve one problem, then other one is easy. You can solve by yourself because it is very simple and same procedure you will follow. So let's see. Let me stop this share. Did you see a MathCAD file? Hello?
Yes, sir.
Okay, so we can solve it, this one. Okay, it's saying in a two-dimensional incompressible flow, fluid velocity component is given, U, and this is V. Show that flow satisfy continuity equation and obtain the function. So you have to figure out phi function and the psi function. And for two-dimensional, this is the continuity equation. So given U equal to this one, V equal to this one. Continuity equation is this one. Expression of team functions psi equal to what? Potential function equal to what? Then you need to satisfy this equation. So you figure out del U by del X. Then figure out del V by del Y. And it's better also you figure out del U by del Y because you need it for stream function and potential function for psi and phi. So both velocity, you take derivative one time with respect to X and also respect to Y. Then this is continuity equation. So del U by del X will be 1, right? You put over here 1, del V by del Y minus 1. So that means it satisfies the continuity equation. And there will be flow, right? Now you need to derive stream function, equation of the stream function. How can do it? This is given. U equal to this mass, V equal to this mass. This is given in the question paper, in the problem. So you see U equal to this one. You can start with V or you can start with U. So what are you getting over here? Del psi equal to U into delta Y. So what is my U actually? U is this one, X minus 4Y. So del psi equal to X minus 4Y into del Y. Now I take the derivative in the integration in the both sides. So what are you getting? Psi equal to xy because derivative is dy. Xy minus into y, that many y square by 2. Now this is you taking this one del, actually what is this one? Del phi by del y equal to u. So right over here, you can say this is constant, but this might be not constant. If it's constant, then respect to you make derivative with respect to x and y, it is always 0 for constant, right? But what I'm saying, it might be a function of fx. We don't know because this line you make derivative. You figure out the del psi by del x. What will be that value? Del psi by del x equal to, you see, will be only y, right? So y. And this is, we are taking respect to x. There is no x, so this term will be 0. So right over here will be minus 0. And what about this term? This term will be derivative of a function, right? Derivative of function. That means this will be minus del f divided by del x. Okay. Now you might have question in your mind that why I consider function of x, not the y. Okay. But if this one, what is del psi by del y? From here, if you write down del psi by del y, this term equal to u, right? This is equal to u. What is my u? X minus 4y. Okay. Now, you make differentiate respect to x. What are you getting? So you differentiate respect to x. That means del psi divided by del y. I'm sorry, respect to y. You figure out respect to y, then xy. So you get only x minus over here 2y square. So what is you getting? 4y, right? Y square derivative 2y. So you get 4y. What is the derivative of this one? Respect to y. This is only x. There is no y. So you take it derivative with respect to y, then derivative of this function will be 0. So I am getting plus 0. What I'm saying, even instead of constant, I am saying fx, because it might be, I don't know, it might be a pure constant or it might be a function of x, because the derivative del u by del y already given. That means this is a function of fx, or it might become a pure constant, I'm not sure. So that we just put a function. Then you make derivative this one, del psi by del x. Now del psi by del x equal to what? Look, del psi by del x equal to minus v, right? So del psi by del x equal to y plus this one. Now minus v. So minus v plus y plus del f by del x. Now, what is the value of the v? Value of the v is given over here. So in left side, you put the v, right side remain the same. So from here, you figure out this value. Just rearrange the equation. You figure out, you see y will be out. So you figure out del by dx equal to this one. Now from here, you figure out f of x. This f of x equal to this one plus constant. So if this f of x, now you can put it over here. So you put it over here. This is your stream function. Okay. So right over here, if you say only one constant, then that will be wrong, because this is derivative. You take derivative with respect to y, then it remains as giving you the same result. Okay, similarly, we need to figure out the potential function. So for potential function, this is the definition. U is given, also V is given in the problem, right? So first start with this one, U equal to minus del phi by del x. This is my U. Then del phi equal to U into del x. So this one, U is over here. Right over here is a minus sign. Then you differentiate both sides. You remember, you differentiate right side is x, right? So you, instead of constant, you add a function fy. You add a function fy, then you differentiate again respect to y to bring this term. With respect to y, then you'll get 4x df by del y. Then just rearrange the equation. The x will be out, this term will be this one. So from here, f of y equal to this one. This f of y is substitute right over here. Then you are getting this one. Okay. Now, how will figure out that it is a incompressible or irrotational flow? You figure out the Laplace equation, and it is saying two-dimensional flow, right? X, Y direction. So you say omega z, you figure out omega z, what is coming 0, then it will be irrotational. You just figure out del v by del x from here, del v by del x minus 4. Then you figure out del v by del y. This equal to minus 4. So difference will be 0. Similarly, you figure out the phi, you figure out phi del phi by del x, then del phi square by del x. You see what is the value coming. So you put all the value over here, is coming 0, that means it satisfied Laplace equation. So there will be no flow is incompressible and no rotation. If satisfy this one, and this one represent flow is incompressible and also irrotational. And problem 2 is the same thing. No, it's a proof that flow is incompressible and irrotational. So you have to satisfy this equation, continuity equation, and this one, rotation along xy direction. Then you figure out stream function and figure out the velocity potential function. Okay, that's very simple. Any question from here? No? Hello? Any
No, sir.
question? No question? Okay. Do you want 5-minute break? Or I'll continue. Hello? Mr.
Yes, sir, sure.
Ijaz, you want 5-minute break, right?
Yes, sir.
Okay, come back at 12:50. Then I will take might be 25 or 20 minutes. Okay. So I put the stop the recording, resume recording. Okay. So this is a very famous equation in fluid mechanics, and Bernoulli's name is everywhere, and also in the solid mechanics you might see Euler-Bernoulli's equation. That is, you need to derive the deflection in the beam, also in the column. Okay, so he derived some equation in also in the fluid mechanics. So what he did, he derived a relationship between the fluid pressure, velocity, and also elevation of the fluid. And it is valid in the region of steady and incompressible flow, where no friction or frictional force is negligible. And it's saying approximate relation, because of Bernoulli's, when he derived, he didn't consider the friction of the fluid. So if you don't consider the friction, then relationship might be not be is not accurate. But still, then later on, somebody add the friction of the fluid in the Bernoulli's equation. So it's saying, despite simplicity, it has proven to be a very powerful tool in the fluid mechanics. Okay, and how will derive the Bernoulli's equation? Again, we'll apply the knowledge of your engineering mechanics. That means we'll apply the Newton's second law to a fluid element, and that fluid element is flowing in a streamline in a flow. Then we apply the how a fluid particle is flowing from one location to another location. Either somebody pushing from the behind, or who is that person, or what the property in water in the river flowing north to south in our country. But why? What is the reason? Is somebody pushing by hand or any other reason? That we need to figure out. As a fluid mechanics student, you can say pressure at point right over here is higher than this side. So he push the fluid toward the right. This is one reason. So that means pressure force is working or pushing the fluid to move around. So in Newton's second law, we know that F equal to M into A, right? So F is force. So, but we are talking about the pressure. But from the pressure, we can figure out the force because pressure P equal to F by A. So F equal to P into A. So we'll get the force. And acceleration actually equal to V del V by del T, right? And the V, if the streamline, if along the streamline, if I say distance S, the fluid particle right over here, next time he's coming over here. So his velocity, I can say function of S and T. That means space and time. So let's see how we can derive. Before we derive, we have to consider some assumption like steady flow. Flow is incompressible. Then we are thinking density constant, and there is rotation of the fluid. And frictionless fluid, that means no viscous effect. Newton's law of viscosity is not work there because there is viscosity considered is negligible or zero. No addition of shaft work to the fluid. For example, you are sitting in a room, you might have AC. So some energy is added to the air. That means cold air is coming out with certain velocity. Or you might have a fan. That means you have a fan. What fan does? He adds some energy to the fluid. That's why fluid is air is rotated around our body, and we feel take out some heat from our body, and we feel comfort. Other thing, negligible heat transfer. We are thinking there is no heat transfer from the fluid. For example, you are in a room by a kitchen, and other side somebody cooking for all day. So heat is transferring from the kitchen to your room, or your office room might be by a boiler. So some heat coming from the boiler room. And so we are thinking no heat transfer, no shaft work in the fluid, and flow along a streamline. That means fluid particle flowing in a streamline. Those are the assumption to derive the Bernoulli's equation. Now, how we can derive? We are considering motion of a small cylindrical fluid element. That means kind of a small cylinder. You look right over here. So obviously it has a radius and it has a area. We are thinking this one is flowing in a streamline. That means he is traveling from here to along this direction. So consider motion of a very small cylindrical fluid element in a steady flow field. That means velocity is not changing respect to time, right? Steady flow field. Applying Newton's second law, which is referred as linear momentum equation in fluid mechanics, in the S direction on a fluid particle moving along a streamline is shown in the figure below. So what we'll do, we'll figure out, in this fluid element, we apply Newton's second law, that summation of F working along streamline will be equal to the mass of the fluid particle into his acceleration. Now, why this fluid particle moving in the right direction, along this direction? Because somebody pushing him from the behind. That means that is the pressure energy pushing him along this direction. So if we are thinking, this is a cylindrical fluid element. So we are thinking right over here, area is dA, right over here, area is dA. So if force equal to will be how much? Force will be area into pressure, right? So we are thinking pressure right over here is P. So what will the pressure right over here? Obviously less than P. That might be, we can say P minus dP, less pressure, right? But instead, what does it mean? That 2n, pressure is not the same. So instead of P, we are saying dP. But still fluid particle is moving. That means the dP value might come negative, okay? But for simplification purpose, we are thinking in the left side, pressure is P, and right side, pressure is P plus del P. And this is not hamper our result, okay? This just come, might be negative sign. Now, you see how much force working in the left side? Pressure into area, that means P into dA. How much pressure working in the along the opposite direction? P plus del P into dA, right? At length of this fluid element, we are thinking ds. And even in small dimension, still this fluid element has weight W. So this weight is working directly vertical. And I am drawing a line, this one is perpendicular to the length of the fluid element. And this angle is theta. So you see, so there is three force total working. Left side, he is pushing fluid element toward upward direction, P into dA. At the upper end, pushing him down, P plus dP into dA. And they have weight of the fluid working downward. So weight of the fluid, how can figure out the weight of the fluid? If you know the volume V, then multiply by rho, you get mass. Then multiply by G, that this will be weight of the fluid. Now over here, weight W. How is the volume of the fluid? Obviously, area into length. What is the area we are thinking? The dA of the, because this fluid element, that means cylindrical shape, very small area, we are thinking dA is the area. And what is the length? ds. So this is given volume. This volume you multiply by the rho and the G, that is W. This W working downward. Now, if you take summation of force along streamline, along direction or length of the fluid element, then how many force you have? You see P into A working dA, P into dA working upward. I'm saying upward is positive. Then minus, right over you have P into dP into dA, right? Then weight, where is weight working? Which direction? You see this weight, I can divide into component. One component working along this direction, other component working along this direction. So W sine theta, this will be W sine theta, and along this direction will be W cos theta, right? So this W sin theta pushing him, try to him down. Okay. So these three force, P into dA, P plus dA, W sin theta is working along the streamline, and they are balance each other by this equation, that summation of all these force will be equal to mass into acceleration of the fluid, because it's no more static, it's moving. Now tell me, who is balancing this force? W cos theta, working along this direction. Who is balancing? If this not balanced, then what will happen? Fluid movement gradually, he'll move forward and also come down, because he's trying to pulling him along this direction, right?
Sir,
So who is balancing?
sir,
Yes.
we have classes now.
Okay, we'll stop it. Just tell me, who is balancing W cos theta? Anyone?
Reaction force perpendicular.
Reaction force.
Opposite.
This is floating, right? Your fluid element is moving around your in the fluid field. So what the reaction? It is not reaction like in a cantilever beam or simple beam. A little bit close. Let's consider one more thing.
স্পর্শক বরাবর velocity,
Not velocity, buoyant force, right?
yes sir,
Because buoyant force or pressure force, if you think the fluid element kind of solid, then what will happen? Pressure force will work buoyant force along perpendicular to the surface. So this will be balanced by the buoyant force acting on the fluid element. But we are considering along motion of the fluid along streamline. So we will not think about this force. So we have three force, P into dA. Then this one, P into dP dA and W sin theta. Okay, in the next class, with these three force, we will work and we will derive the Bernoulli's equation. Okay. So we need to keep it here because you have the classes, right?